All right, welcome back to our second video this week. Today we're going to deal with two parallel infinite sheets, which this is also a sneak peek into capacitors. So that's what capacitors are. It's just two sheets or plates of charge with a distance d between them, and we're going to be going over that soon. So this is a little sneak peek, but we're going to find the E field between the two plates, and then we're also going to find the potential between the plates. More specifically, we can find the potential difference between them, but we'll go through and find just the potential. So yeah, let's just get right into it. So I have a positive plate or sheet on the left hand side, and then a negative one on the right hand side. So the first thing I'm going to do is draw the electric field lines for both of these. So if you remember in the last video, these kind of work just like any other like a point charge. So positive flows outward and negative flows inward, and more specifically, each flows from positive to negative charges. So we know that kind of for this positive plate, there's going to be an E field that points like this. And then we can imagine on this side that there's also one like that goes to that way, because they're both positive, right? On each side of the sheet, it's both positive. And then for the negative, we can imagine, since it's flowing on the right-hand side, it's flowing towards the negative. So that way it's going into it. And then if you notice, when we're drawing the field lines for the negative, it's flowing in the same direction as the positive one. So you can imagine that this negative one will have a continuous like charge that's going towards it, going this way, and it will continue to go this way. And then also the positive will have a continual electric field line that goes out that way. So what happens, what we see is that in, let's call this region 1, 2, and 3. In region 1, but all of the electric field will be canceled out. So there will be no electric field over here. And also the same thing happens in region 3. No electric field will be going on there. There will only be field in region 2, which is very cool. So yeah, now that we've talked about that, let's talk about finding the electric field in between these two plates. So let's do that. Okay, so just like before, I drew our Gaussian surfaces on each of these plates, and we're going to find the E field for the region 2 up here. So we do have to treat these separately at first, but we can then combine them together to find the total E field in this part here. So we already decided that when we combine them in regions 1 and 3, it's going to be 0. But let's start by thinking about, let's go back to what we did last video, and let's focus on each of the plates separately, and then we can combine them together to find the total E field that's just in the middle that we're looking at. Okay, so if we remember from last video, we are going to use the cylinder just because we love our different surfaces like that. So I'm going to draw these dA vectors. So let's look at the positive one first. So I'm just going to do positive here. So if we remember, this is going to be just like the last video with our positive charge that we did. So our E dot dA, they're in the same direction. So it's going to be our electric field becomes, so let's write out Gauss's law first, I guess. That's Gauss's law. So let's now look at the first region. So like this, let's call this region 1 and 2. 1 and 2. Okay, so now we're going to do exactly what we did last time. So we already know that this is going to have the electric field is going to have a contribution from these two circles that have the same direction of charge. So what's going to end up happening is that we're just going to end up with a value that kind of looks like E times 2 dA equals Q enclosed over epsilon naught. So now, like I said, E is a constant, and so we can take out that E, and we're left with 2 times the area of our surface, which is just a circle, and we know what that is, which is pi r squared. So we're left with that E equals, or we're left with E 2 pi r squared equals Q enclosed over epsilon naught. And we already know, and we've already decided that since sigma is equal to Q over A, our Q enclosed is just going to be, sigma pi r squared, because that's the area of one of the circles. And so what we're left with is that E for this positive one is just going to be sigma over 2 epsilon naught. So there's that. So that's for this one right here. We've decided that the E sigma over 2 epsilon naught. Okay, so that's for the positive one. So I know that the negative one looks a little bit daunting, but just remember that for these electric field lines, they keep flowing, right? So I know I kind of drew it like this, but what's really going on is something like this. So this one is kind of flowing like that, and then this one is flowing outwards like that. So they just keep flowing, right? So it can look like kind of more like that. So in region 1, we can see that our dA vector right here still has this component right here that is the electric field going in the same direction, as well as this 2 over here has this portion over here where it's still going in the same direction. So for the negative one, it is exactly the same. We are still left with that E equals sigma over 2 epsilon naught. So that is the field contributed to both of these parallel plates. But what if we wanted to find the E field between the two of them in this region 2? Well, we would just add them together because they are contributing the same constant E, and so we can add them together. So the E from positive sigma plus the E from negative sigma equals our E total. So we get sigma over 2 epsilon naught plus sigma over 2 epsilon naught equals our E total. So this is just, since they have the same denominator, it is just equal to sigma over epsilon naught, which is very useful for us. So there we go. That is the E field between two parallel plates. It's just sigma over epsilon naught. There's no dependence on D, which is crazy, right? Okay, so let's clean this up a bit, and then we'll solve for the potential. Okay, so now we want to solve for the potential difference. So let's just go for it. So, okay, so our potential difference, delta V, is defined as E dot dl, where dl is some vector. So what we are looking for is this delta V. So we've already solved for our electric field in region 2, which is what we're looking for, the potential in region 2, this region 2 with this distance d. So just like Gauss's law, we want this dl to point in the same direction as our electric field, because if you can notice, this is a dot product. So we want them to be in the same direction. So we can imagine that we want our dl vector to go like this. It's flowing from positive to negative, just like the electric field is. And so now we can be left with E dl. And we already know that our electric field is constant in this field. That is how we solve for it, because the electric field is constant from the positive plate and the negative plate. So when we add them together, it's still constant. It's just double what it was before. So what's changing is this dl, which is just a length, an infinitesimally small length that stretches from the positive to the negative. But we are already told what that distance is, and it's that distance d. So we know that we know what our E is, and now we know what our dl is. It's just that when we integrate over this distance dl, we are left with d. So we are left with sigma d over epsilon naught. And that's it. So from this plate to this plate, our potential difference is sigma d over epsilon naught. So now that we've solved for the potential difference, let's think about what this means practically. Okay, so now that we've solved for the potential difference, I want to talk about one important thing. So this is our E field vector right here. It's flowing from positive to negative. So let's imagine that we have two different particles that are traveling in this capacitor in between the two plates. So let's imagine that one of them is a proton, and let's say one of them is an electron. So one of them, these are not the same size. Okay, so let's imagine that both of these are starting from the positive and then they're moving towards the negative plate. Which one will have an easier time moving in this electric field? Is it the positive or the negative charge? It's the positive charge. So the positive charge will have an easier time moving in this electric field than a negative one, because the electric field is flowing from a positive charge to a negative charge. So when the electric field is moving from positive to negative, the positive charge is going to want to kind of follow that path and move towards the negative plate that's on the right. Whereas the negative charge will not want to move in the same direction, because that's going towards a negative charge. That's going towards a negative sigma on the right-hand side. So really, it's going to feel pulled away from that negative charge. It doesn't want to go anywhere near it. It's going to want to go towards the positive sigma over on the left-hand side. And so that is kind of a little intro into kind of capacitors and also the flow of current, and kind of how that all ties in together. So keep that in mind. When we're talking about different electric fields, it's usually in the direction that positive charges will flow, not negative charges. So keep that in mind. And remember that when you're going through your homework or any other types of stuff like that, electric fields indicate where positive charges will want to go, not negative charges.